So we're going to discuss asymptotes using the concept of a limit. You have analyzed asymptotes. You've dealt with asymptotes in previous math classes. This will be hopefully a little more conceptually easy to understand instead of just memorizing things. And with this notation, maybe it's a little new to you. So what is an asymptote? Well, we have vertical asymptotes and horizontal asymptotes. This graph has a vertical asymptote at x equals a and a horizontal asymptote at y equals b. X equals a being a vertical line. Our function is getting very, very close to x equals a. It's going up and down as we approach a. And at y equals b, we have a horizontal asymptote. Okay. And what we're going to do when we're trying to look at vertical asymptotes is we will find that it's when the limits of certain functions, certain one-sided limits actually, when they approach positive or negative infinity. Our goal is to be able to take a function, find the location of a vertical asymptote, and then understand the behavior of our function around the asymptote. Okay. Now, you come up here to that vertical asymptote, and if I asked you what is the limit as x approaches a in general of this function, we'll call this function f of x, you'd say it does not exist. You'd say we have a vertical asymptote. We are not approaching a value from the left and from the right. We're going straight up and straight down, so the limit doesn't exist. However, if I asked you what was the limit as x approaches a from the left, you would tell me that as we get closer and closer to a, this input value, that my function is going further and further down to larger and larger negative values. We'd say that we'd be approaching negative infinity to the left of a. And if I looked at the limit as x approaches a from the right of a, my function values are getting bigger and bigger and bigger, approaching larger and larger positive values. We'd say we'd be approaching positive infinity. Okay, so our goal is locate a vertical asymptote and then figure out, which direction my function is trending as we get closer and closer to the vertical asymptote. A horizontal asymptote, we will find them when we evaluate the limit as x approaches positive or negative infinity. This is new to us. We're having infinity in our limit. We are used to having values, specific input values. But we're saying what is going on all the way to the right and all the way to the left. We are trying to focus on our end behavior of the function. So I would look and analyze what is going on all the way over here to the left. We'll call this all the way over to the left negative infinity. And all the way over here to the right, call that positive infinity. And to analyze the end behavior, we're going to have to look in both directions. The limit as x approaches negative infinity, looking at it by itself, not plus or minus infinity. And for this function, as I get closer and closer to negative infinity, my function is approaching this y equals b line. So we'd say I have a horizontal asymptote. To the left, my function is approaching b. If I look to the right, as x is approaching positive infinity, my function is trending upwards. As I get further and further to the right, my function is going up. So it's approaching larger and larger y values. We'd say it's approaching infinity. This is telling us to the left, I'm approaching b, but to the right, I'm going up. That's the end behavior. That's what we want to figure out for any function that I present to you. All right, and we are actually going to start with horizontal asymptotes. Take a little bit longer than vertical asymptotes. So skip a couple pages because it's not in the correct order, and go to horizontal asymptotes. Okay? That's very important. If I ask you, find a horizontal asymptote, you need to do two things. You need to evaluate the limit as x approaches infinity and the limit as x approaches negative infinity. Okay, that's key. A lot of times, and you'll see in these notes, most of the questions will tell you which direction to look at. Okay, but in general, if I ask you to find a horizontal asymptote, this is what you're going to do. Now, how to do this, we'll get to. Okay, and I was going to go into this a little bit more if we already knew about the vertical asymptotes, but for right now, I'm just going to leave it at that, and we'll go into it. Now, you guys have dealt with horizontal asymptotes. You guys have dealt with end behavior of functions before in previous math classes. There are math teachers that like to use acronyms, things that you memorize, and memorization I don't love in math because it's not conceptually driven. It's more just like rote memory driven. And you guys might have heard about the Bobs in the past. Bob yo, Bob no. I'm not sure. I don't know anything about the Bobs. But if you know the Bobs, you know this stuff. But hopefully the way I approach this with you will help your understanding of why the Bobs work. Okay? You with me? Great. Now, can you use the Bob in the future? Sure. If you love Bob, hang out with Bob. If this helps you understand Bob, great. If you don't want to use Bob anymore, great. You can do that too. Okay? The key for these limits, for these horizontal asymptotes, is we're plugging in big numbers, people. Infinity. Okay? We're plugging in large values. Now, it's tough for us to understand large values. We think of a billion as being a large number. That's not a large number. 1 followed by a billion zeros. That's a large number. That's what we need to start thinking about. And what I'm going to tell you is that, and it's not really the highest powered term, I'm going to say the fastest growing term. The fastest growing term of a function is the most influential when we're plugging in these large values. And because of that, if I evaluate this function, 2x cubed plus 1,000x squared over 10x squared plus 5x minus 3, when looking at this, since I know when I cube a value, it's going to grow faster and faster as I plug in larger and larger values. So much faster than if I square that same value. Because I know that, I can actually just cross that sucker off and say, don't worry about it. It's insignificant. It is like adding a very, very small decimal to a very, very large number. But you're probably thinking, but Mr. Messner, like 2x cubed, that's going to be a big number. 1,000x squared, that's going to be a big number too. When I add them together, aren't they going to, react with each other and like add to be a new big number? Well, let's kind of investigate this. Like, let me show you that you can cross out 1,000x squared. I'm going to go to my friend Wolfram, and Wolfram likes big numbers, likes doing calculations. And I'm going to compare if I take big numbers and plug it in to 2x cubed, and if I take big numbers and if I plug them into 1,000x squared. Okay, and the first number I chose to plug in for x was 10,000. If I took 2 times 10,000 cubed, I get 2 trillion. Okay, that's a relatively big number to you guys. And if I took 10,000 and plugged into 1,000x squared, I get 100 billion. Well, if I add 100 billion to 2 trillion, isn't that going to change 2 trillion? Like, doesn't that make a bigger number? Why are we saying you can ignore it? Well, how much bigger is 2 trillion compared to 100 billion? What we can do is divide the two together to see, like, how many times does 100 billion go into 2 trillion? And when I divide those two numbers, I see that it's 20 times the size. Okay, so it's actually a lot larger. It's 20 times bigger. Now, if you think about taking something and adding something 1/20th of the size of it, how much is it going to change? Well, that's kind of conceptually like adding 1/20th to 1. And if I add 1/20th to 1, I get 1.05. Okay, so I made a bigger number, sure, but it's just a little bit bigger. Okay, but it's still 1.05 compared to 1. It's still different than 1, but we weren't plugging in large values. Okay, what would be a large number? A Google. Anybody know what a Google is in terms of its numerical value? We guys know the website, we know the search engine, but the name came from the number.
Isn't it like 1 with 100 zeros after?
It's 1 followed by 100 zeros. You can express it as 10 to the 100th. 10 to the 100th is the Google. So instead of 10,000, let's plug in 10 to the 100th. And let's cube that and then multiply it by 2. Okay? So I took 10 to the 100, cubed it, multiplied it by 2, and I get this number. This number is 301 digits long. Now we're starting to talk about big numbers, okay? Well, let's plug a Google into 1,000x squared. I plug in a Google into 1,000x squared. There's the Google plugged in. I get something that's 204 digits long. So we're talking about 300 versus 200 digits. Okay? Well, it seems like you're adding a 200-digit number to a 300-digit number. It's going to change that 300-digit number. Well, let's look at the relative size of those two numbers by dividing. So dividing the bigger number by the smaller number, turns out this bigger number, the x cubed, compared to the x squared number, is 20, this has a name, untrillion the size of the smaller number. It's this many times larger, this number than that number. Which means if you add them together, what would that be equivalent to if I'm adding a number to 1? It's equivalent to adding 1 over 2 followed by this many zeros. You can't even see it. It keeps going. I counted it out. That's 98 zeros right there. Okay? Which means if you add those two numbers together, this is what you get. 1.98 zeros and a 5. Now, you're thinking 300-digit number plus a 200-digit number. That's going to be a bigger number, right? A much bigger number. No. It's like adding a very, very, very small decimal to a very, very, very large number. So, after that demonstration, you should feel comfortable with saying, nope, that's not going to do anything. If I'm plugging in large values into 2x cubed, plugging in large values to 1,000x squared, will be just adding a very small decimal to a very large number. And if you look at the denominator, 10x squared, 5x, 3, 5x isn't doing anything. Adding a small decimal. Subtracting 3, yeah, that's not going to change things. We are essentially 2x cubed over 10x squared. Now, if I ask you to find the limit as x approaches infinity of this, your first instincts would be to simplify that. It looks like I got x cubed over x squared. I can change that, and I can make that to x over 10. I don't even bother simplifying the fraction into 1 over 5. Okay, now if I plug in infinity, and this is similar to the limits from the first unit, we want to try to plug in the value until we understand what's going on. Well, if I plug in infinity, you can see 2 times infinity over 10. This is a number, okay? 2 times infinity is a very large number. Divided by 10 remains a very, very large number. We say we're approaching infinity. So this means for this function, as I travel to the right, this means I'm going up. Or the end behavior of this function is like that, to the right. Okay, now, if I plugged in infinity anytime before that, like right here, and I get infinity over infinity, this is kind of like a 0 over 0. When you got 0 over 0 with your limits from last unit, you would have to do more analysis. Well, do more analysis when you get infinity over infinity. Either simplify, or you can be able to just kind of see what the answer is by comparing growth of functions. Okay, so this means do more. Put our phone all the way away, please. We need to be careful though. Let's change this to a -4. If I asked you to find the limit as x approaches negative infinity, so this is asking you what's going on with the end behavior on the left for this new function. Well, with our new acquired knowledge, we may get rid of the -20x. It's insignificant compared to what the 4x cubed is doing to the large numbers. We can get rid of the x. It's not going to make a difference. It's adding a very small decimal to a very large number. And if I asked you to find this, your first instinct is to simplify it. And when you simplify this, you get -4x over 1,000. I don't even bother with the fraction. But I'm finding the limit as x approaches negative infinity. Well, if I plugged in negative infinity, it's important to keep track of our signs. We think, oh, negative infinity would lead us to negative infinity. But a negative times a negative gives us a positive large number. Divided by a positive keeps it as a positive large number. So this is actually approaching positive infinity. Okay, so plugging in to make sure you have the correct signs in the correct direction, very important. This tells me that if I look to the left, I'm going up. So that's the end behavior to the left with this function. Stay with me, Mr. Stardy. I believe we're almost at lunch. You can fuel up when you get there. All right, so that right there is one of the bobs. I know there's some bob that explains when like the numerator's faster than the denominator. I don't remember it, but I never learned it. But there you go. That might help you understand one of the bobs. Next one. Let's say after simplifying, we notice that we have a higher degree term in our denominator. Well, first we need to understand this situation. If I have a number divided by infinity, let's take like if my number was 3. If I keep growing in a denominator under the 3, what's happening to the progression of these fractions? Getting smaller and smaller and smaller. Getting so small that they are approaching what value? 0. So whenever we see some number divided by infinity, we say it approaches and it gets so close to, this is a very calculus-driven concept, the concept of approaching and getting so close to that you're essentially equal to 0, okay? Something divided by infinity, we're getting closer and closer to 0. Well, knowing that I can cross off this 20, if I asked you to evaluate this limit, you would simplify. And when you simplified, you'd end up with -5 over 2x. And if you plugged in infinity, you'd get -5 over infinity. Well, that's approaching 0. This is telling us that my function, if I look to the right, is going to be approaching 0. How is it approaching 0? From up here, from down here? I don't know. I don't care. For right now, I just know that we're approaching 0. Now, does the sign matter? Go ahead and look at this one. If I approach negative infinity, would that change it? And it wouldn't. It would be the same thing. The sign does not matter in this situation. Limit as x approaches negative infinity. If I know the concept of big numbers and adding very, very small decimals to very, very large numbers, and these are insignificant, that we can do this, and then do that, and then get this. Yeah, I have 5 over negative infinity, but it's the same thing as 5 over positive infinity. I just have very, very large negative numbers. We would just still be approaching 0. Now we'll talk about how we could be approaching 0 from the left, like approaching 0 from the negative side, and 0 from the right when we talk about vertical asymptotes. For right now, you just know the end behavior for this function to the left is we're approaching 0. Where are we coming from? I don't know. I don't really care for now. That's another Bob. Maybe it's the eats DC one. I don't know. But that's another Bob. Maybe that helps you understand. Now the third Bob, another Bob, this situation. What happens after I cross things out? I get that. Well, your instincts, if I gave you that, would be to simplify it. And when you simplify this, the answer is revealed. -4. Now we have a horizontal asymptote other than at 0. This is at -4. Here, if I'm looking to the right, my function's approaching -4. So my end behavior is like that. How are we getting to it? I don't know. Don't worry about it. Now, would it be different if I approached negative infinity? I believe it should be the same exact example. So get rid of this 2 if you guys have a 2 there. Should be the same exact example, only this time I'm looking to the left. So same thing. Cross out, doesn't matter, doesn't matter. That doesn't matter. If I gave you this, your instincts would be to simplify. Now, if I plugged in negative infinity, am I going to get +4? Well, if you plugged in right now, it'd be -4 times negative infinity over negative infinity. So it's like a negative times a negative divided by a negative. That's a negative, which is a negative. But these would cancel out. The negative over the negative cancels. It doesn't matter. You would still get just -4. So for this example, you can say both to the right and to the left, we're approaching -4. Okay? And the same thing happens with zeros. Typically, you'd approach 0 from both directions if you have a k divided by an infinity. All right, so that's another Bob. Now, the questions could be asked like those previously, or I could just ask you, hey, find the horizontal asymptotes. Okay, or describe the end behavior. Just make sure you look in both directions. All right, and go ahead and do these 3 really quickly. Once we kind of cancel out those 1s, we can simplify all 3 of these very quickly and then understand our answers without having to memorize anything. We have to be careful with signs for our first one, but for the other 2, signs won't matter. Okay, I got infinity then negative infinity for the first one. It's because when I plug in a large negative value multiplied by 2 divided by 3, I get a large negative value. If I plugged in a large positive value, 2 times a large value divided by 3, large value, that's positive. The other ones, the signs don't matter. It does not matter if I'm traveling to the left or to the right. For this example, we get zeros, we get 2/3. Okay? If I give you these 3, again, we should be looking in multiple directions. If we just simplify right away for this guy, it should be very clear that we are approaching 0. 1 over infinity, 1 over negative infinity. But we have to be careful. For the other 2, instincts are to cross out that 4 and to cross out that 5. But I'll show you in one situation, it actually does matter. You can't cross it out. Okay, it's because this 4 and this 5 are not in the term with the x's. It's a totally separate term. If I looked at the limit as x approaches infinity for this, yeah, I could cancel this to be x minus 4. And if I plugged in infinity, you'd have infinity minus 4. Well, that's still infinity, so that's not gonna matter, the 4. If I cross it out, it would be fine. But it only doesn't matter because I ended up with an infinity minus 4. If I went the other direction, I'd have negative infinity minus 4. That would not matter as well. Large negative number minus 4, still a very large negative number. So the 4 didn't matter. I still don't want to cross it out. This 5, it's a different term. When it's a different term, leave it alone. It might matter. Let's look at this limit as x approaches infinity. Well, 2 over 1 plus x squared. You can either plug in infinity right away and get 2 over infinity plus 1, which we know 2 over infinity is approaching 0. You could cross out the 1 if you wanted to, and that would work. But we know that 2 over infinity is approaching 0. So we end up with 5 minus 0. Does the 5 matter in this case? Oh yeah, big time. The answer is 5, not 0. So be careful. Don't cross out if you have numbers in other terms. Other terms will matter. If you just have one term like we talked about for the other ones, you can be more free with your crossing out of things. Go away. Different term, don't cross out. Okay, cool. Again, for these, if we're talking about quickly being able to do them, eventually you won't have to go through the procedure of crossing things out and simplifying. You can just see, yeah, the x to the 5th is growing faster than the x to the 4th, which is the only thing that matters. We're approaching infinity. It would help to understand in terms of signs, like if this is a negative 6, then this would be negative infinity, and this would be positive infinity. So maybe change your example so that you know to just be careful with your signs. If I simplify this, it's x to the 5th over negative 6x to the 4th. That goes to x over negative 6. The negative 6 is going to make a difference with our biggest degree term. Okay, the other ones though, you should be able to do after just a glance and an analysis. So the crossing out and the simplifying will work, will help you. These guys, these are interesting. Let's take a look at these guys. Now, I'm going to simplify this. I'm going to need to simplify that. It's important to simplify this, not just look and say, oh, I know what my answer is. I'm going to cross out that 2, insignificant, going to cross out that 1. And I have 3x over root 2x squared. Now, properties of exponents, if I have like xy to the p, that's the same as x to the p times y to the p. The square root is just an exponent, so 1/2 power. So the square root of 2x squared could be written as the square root of 2 times the square root of x squared. It's just 2x squared to the 1/2 power. Okay, well, this guy can be simplified. What's the square root of x squared? Almost. Not just x. It's plus or minus x. Where students have problems remembering that is when they're solving equations like this, x squared equals 9. Well, your teacher tells you take the square root of both sides. And you say, okay, x equals plus or minus 3. So that means the square root of 9 must be plus or minus 3. False. Square root of a positive number is a positive number, and only a positive number. Okay? It is the fact that the square root of an unknown value, or your unknown value, could have been positive or negative. But it's being squared, it becomes positive, you square root it, stays positive. It's important to realize that original value could have been a positive or negative. The square root of 9, that's just 3. It is actually this step that we skip, which we shouldn't, because this is where the plus or minus comes from. And then it gets moved over there. Okay? So, square root of 9, just 3. It's the square root of x squared that is plus or minus x. All right, so we get here, we can simplify these x's, and I get plus or minus 3 over root 2, which means this function with this square root actually has 2 horizontal asymptotes. But it can't have both at the same time. You're not allowed to approach one guy up here and one guy down here at the same time. You're either going to go towards this guy or to that guy. We have to figure out which one it goes to. And we're actually going to go back to this step here. And we're going to check our signs. This step is important because it's before we simplified, change things to a plus or minus. This is when the sign actually counts. Now what we do is we take the infinity, we'll plug it in here, just to check our signs. And we have 3 times positive infinity over root 2 times positive infinity squared. This is telling me that we have a positive divided by this is a positive. The denominator will always be a positive. You're taking the square root of a positive. Okay? This is squared, so it's a positive. So because this is positive when I'm looking to the right, this is telling me that no, I don't have both of them. I just have the positive 3 over root 2. So to the right, I'm up here. Going to the left, let's confirm that we're going to the other one. Hopefully that's the case. Well, again, you're going to get down after you simplify to the plus or minus 3 over root 2. You're going to come back to 3x over root 2x squared, and you're going to plug in negative infinity. Just to check your signs, not to get your answer. You already got your answer down below. 3 times negative infinity is a negative, divided by root 2 times negative infinity squared. Something squared is a positive, times 2 is a positive, rooted stays positive. The square root of a positive is a positive. So I have a negative divided by a positive. That's a negative. That's telling me that to the left, I am going to just the negative root 3 over 2. Now you might think, oh, negative goes to the negative, positive goes to the positive. That's easy. I'll just use that for future. It's not always going to be that case. Everybody do this one. Check your answers with a neighbor. Let's see if we can figure out which one we go to as we travel to the left for this function. Go. You'd start by crossing off the 5. Now, square root of 2 I didn't simplify because the square root of 2 is just the square root of 2, 1.3, I think. I'm not sure. But the square root of 4 is positive 2, so you can simplify the square root of 4 to just be positive 2. After simplifying, you get a negative 6 over plus or minus 2. That is telling you that you are either positive 3 or negative 3. Hopefully we can all get to that plus or minus 3. Once we get there, we have to figure out, if I go to the left, am I going to positive 3 or negative 3? Check your answers with a neighbor. Which one, Mr. Townsend, the positive 3 or the negative 3? That's the question. Yep. Boom, 5's gone. Negative 6x over root 4x squared. Rewrite it as negative 6x over root 4 times root x squared. The square root of 4 is just 2, just positive 2. The square root of x squared is plus or minus x. The x's will cancel, giving me negative 6 over 2, but with the plus or minus ends up being plus or minus 3. I go back to this guy to check my signs. If I plug in a negative value, a negative large value, negative infinity, in here, I get negative 6 times negative infinity over root 4 times negative infinity squared. Negative times a negative, a positive, divided by a positive. The square root of a positive number is just a positive number. So, positive divided by a positive gives us a positive 3. Okay? Fantastic. Those are a little bit more difficult, but all of those are kind of easy. Let's throw in some trig functions. Now, let's look at the limit as x approaches infinity of sine. Well, the first question I have is the sine of infinity infinity? Discuss that with your neighbors. If I plug in larger and larger and larger values into sine, do I get larger and larger values out of it? All right, let's see if you guys are right. I'm going to plug in larger and larger values into sine. We'll start at pi. Not a large value, but we'll start there. What's the sine of pi? 0. 0. Sine of pi is 0. We're over here. We're not going up or down at all. What about 2 pi? Getting larger here. What's the sine of 2 pi? 0. So, okay, pi, 2 pi. All right, let's go to 1,000 pi. Okay, it's 0. Okay, sine of a Google times pi. Okay, so it doesn't look like if I'm plugging in larger and larger values into sine, I'm going to get larger and larger values. Okay. Now, what about a pi over 2? What's the sine of pi over 2? What's the sine of 3 pi over 2? All right, so what is the maximum value? I'm not sure where we end up if I do the sine of a Google times pi over 2. It's either 1 or negative 1, right? And that's a large value. So does sine of infinity equal infinity? No. It's at most 1. It's at least negative 1. I froze up. We're back. So if I asked you the limit as x approaches infinity of sine, is that infinity? You'd say no, it doesn't exist. It oscillates, it keeps going up and down, it doesn't grow. And that's important to know, that sine, cosine, they do not grow. All right, so let's look at the second one. The limit as x approaches infinity of sine x over x. Now your instincts are screaming at you to answer 1. It's like sine x over x, that's 1, right? But you remember from your test that like anything other than 0, it's not 1. Okay. Well, what is it if I plug in larger and larger values into sine x over x? Discuss that with your neighbors. Here's an easy way to think about it. Let's start plugging in values into sine x over x. Well, in the numerator, I know it's at least -1, at most 1. So this is what's going to be the numerator no matter what I plug in for x. Well, if I grow my numbers in the denominator, 10,000, 100,000, a Google to a Google, that's a big number. Okay? That's like really big. What are we trending with these fractions? We're getting closer and closer to what? Yeah, 0. All right, we'll do the next one. Now that we know that, it's actually tough to see that that's getting closer and closer to 0. People like to see more. Pretty close to it, wasn't like a change. Yeah. What about the next one? Discuss that with your neighbors. Because the numerator is somewhere between -1 and 1, while the denominator keeps growing. What's happening to these fractions? No matter what is up here, it's some number between -1 and 1, divided by an ever-increasing number. Pick a number between -1 and 1.
1 or -1.
Okay, so you pick -1. What if these were all -1s? What's happened to these fractions as I go? Okay. Getting smaller, right? What are they getting closer to?
0.
Okay. Pick another number between -1 and 1. Is the same thing going to happen? That's why. There's only one answer.
I was just seeing in my head like sine pi over 2 or like negative or something.
Sure. Yeah, but plug in bigger numbers. We have to not just plug in one number. We have to plug in larger and larger. We're plugging in infinity, not just one value. So it's the thought process is not what do I get one time, and what do I approach as I plug in bigger and bigger and bigger values. Okay? So no matter what value I plug in the numerator,
Looking for a fluctuation.
well, it's going to be positive and negative, but it's approaching 0. So the fluctuation is that like the fractions are getting smaller and smaller, but yes, exactly, just like that. What do we get? Who's got it? Raise your hand if you and your neighbors got it. Mr. McDonald.
1/2.
1/2 is correct. How'd you get 1/2?
Sign of x will be 1 or -1, so it doesn't matter. And cross out the x.
You can cross out the sign of x. The sign of x is not going to make a difference, okay, compared to 2 times x. It's like adding at most 1 or subtracting at least -1. So we just have x over 2x. Well, that's just 1/2. Very nice. What about the next one? Cosine of 1 over x. Again, sine does not grow. So that is why, since sine does not grow, 2x grows. 2x will get bigger and bigger. Sine won't. Cosine of 1 over x. What do we get for that one? As x approaches infinity. What do you think, Miss Behrens? What did you get? 1. How'd you get 1 out of that? That's it. Okay? This guy, don't worry about this guy right now. We'll come back to that guy. All right. Now, we will get to situations where simplification is not going to help us. Like if I looked at the limit as x approaches infinity of x cubed over 3 to the x, or 3 to the x over 4 to the x, or e to the x over log x. I can't simplify this. I can't even simplify this. Okay? So it's like I can't get to infinity over a number or a number over infinity. Instead, we're going to have to think more conceptually about what's going on with the growth of our terms. Okay? Let's go back and think about the fastest growing thing. If we have, not necessarily a degree, but a faster growing term in a numerator compared to a denominator. Faster over slower. Now, we'll get infinity over infinity because they're both growing. So they're both going to produce bigger and bigger values. But watch what happens. If I have something that's maybe like multiplying by a factor of 10 in my numerator. So that's like pretty fast growth here. Whereas my denominator, it's growing, but not very fast. It's growing by 1. What's happening to those fractions as I continue to grow? Getting bigger and bigger and bigger. If we have faster over slower, we're going to approach infinity. Not necessarily like infinity over a number. If it's just faster over slower, we're getting bigger. If we have something that is slower, growing in the numerator, over something that is faster. Let's think about situations like this where the faster growth is in a denominator. And the slower growth is in the numerator. So my numbers in the denominator growing much faster than the numerator. Even though we're growing on both the numerator and the denominator, what's happening to these fractions? Getting smaller and smaller and smaller, approaching 0. Okay? So we have to use that conceptual understanding for limits like these. We have to know that 3 to the x grows faster than x cubed. 3 to the x actually grows faster than x to the 3,000. 3 to the x grows faster than x to the 9,000, 99,000. Now you might be thinking that doesn't make any sense. Like, if I plug in something like 3 cubed is smaller than 3 to the 3,000, right? Right. What I'm telling you is that 3 to the x will eventually catch up with x to the 3,000 and beat it tremendously. Let's do a little experiment. Again, if I do 3 to 1,000, yeah, that's a big number. 478 digits long. It's this number. Okay, that's 3 to 1,000. That's definitely bigger than 3 cubed. Three to the third. Okay, 3 to the x power. 27. This wins. Watch what happens when I put 9999999. I think that's big enough. 9999999. 7 numbers. So 9999999, so 9,999,000, is this number. It is 7,000 digits long. Exactly. If I do 3 to the 999, let's see how many digits this is. 4,771,213 digits. Okay? You didn't believe me, and you're like, 7,000 digits, yeah, that's boom, already beat you. And we're only at 999,999. That's not even a big number. So 3 to the x wins. Now, you think, oh, 3 to the x and 4 to the x, do they grow the same? No. 4 to the x will grow faster than 3 to the x. You can't simplify 3 to the x to the 4 to the x. You'd say this is faster. E to the x and log x, we'll talk more about e to the x and log x, but e to the x wins. What's that telling you? If you're trying to evaluate these limits for all 3 of these, you're going to get infinity over infinity. You can't simplify it, but you know that this is approaching 0 because 3 to the x wins. This is approaching 0 because 4 to the x wins. This is approaching infinity because e to the x wins. Faster growth over slower growth over faster growth. Okay? So now we're moving into more theoretical territory. Now we have to talk more about log and e to the x. E to the x is the most common base. E is the most common base of an exponential function. And we'll be using e's frequently and e to the x frequently in this class. Okay? Its arch enemy, its nemesis, its inverse is the log function. They are inverses of each other. E to the x is an exponentially fast growing function. It's an exponential function. The log function grows exponentially slow. The log function, and we'll do more with e's and logs in the future. The log function right now, all you need to know is that it's the slowest growing function. It grows slower than x to any power, including all fractional powers. Okay? It will grow slower. And that's important because it's important to understand which is the fastest and slowest functions. So we're going to go and list them off from slow or no growth to our fastest. And if we just have a number, there's no growth. If we have sine or cosine, no growth. But a log function would come next. It will grow, but very, very slowly. You have to plug in e to larger and larger powers to get larger and larger values. Then we have x to a power. Then we'll have a number to the x power. That's pretty much where we stop for this class. If you end up taking the BC test, we talk more about factorials, which is faster than x to a power. And we don't ever talk about this one, but that would be the fastest. We usually stop right here. Why don't you guys go to lunch, and then we'll finish this off later. We have the growth of functions. And being able to just compare growths are how you're going to be able to tackle those that you cannot simplify. So you should be able to look at these 3, understand, oh, this one grows faster than this one. It's in the numerator and the denominator. Figure out if this is going to be an infinity or a 0. So which one of these is 0? Figure that out and check with your neighbor. So log x is the slowest growing function. So faster, under slower, that guy is approaching 0. This guy and the other one both would be approaching infinity. Okay. We have to be careful. We see A limit like this, x approaching infinity. All the other examples, we just started crossing out what was to the right of the first one. But in this case, we know that 3 to the x grows faster than x to the 99th. That didn't work. So cross out the x to the 99th, leave the 3 to the x. Then you can have this one simplified, but only to here. And from here, you must compare the relative growths. What's bigger, E or 3? 3. E is 2.717, if we recall. So this is approaching infinity. Thank you. Now, these exponentially fast-growing functions, they throw a wrinkle into things. If I approach positive infinity with 3 to the x, I go to positive infinity. We just grow. But if we are going to the left towards negative infinity, a lot of students assume that we are going to negative infinity. But this is wrong. What is the limit as x approaches negative infinity of 3 to the x? 0. Because if we plug in that negative infinity, I get 1 over 3 to the positive infinity, remembering your negative exponent rules. And we know that this is like a number under infinity, which is approaching 0. So that causes problems, because if we look at our growth of functions, we say that's the fastest, but this is only as x is approaching infinity. If I went in the other direction, if x was approaching negative infinity, all of a sudden this guy goes all the way down to the bottom, and it is a no growth function. So that ends up being on the bottom. Yes? Just that guy. And stop there. So this is when we could have multiple horizontal asymptotes that are not just an infinity or a negative infinity. Take a look at e to the x times x to the 10th. Find the horizontal asymptotes. Well, I find the limit as x approaches infinity and the limit as x approaches negative infinity. That's the key to finding the horizontal asymptotes. Figure out the end behavior. What's going on to the left and to the right. Now, if I plugged in infinity, it would be e to the infinity times infinity to the 10th. That, you should know, is just a very large number. But plugging in negative infinity, we get e to the negative infinity times negative infinity to the 10th. We know that can be simplified as 1 over e to the positive infinity times negative infinity to the 10th. Now, it's infinity over infinity. What to do? Do we say does not exist? No, we analyze more. So we think about the relative growth of the functions. Something to the 10th power will grow slower compared to e to the power. And all of a sudden, to the right, we are approaching positive infinity. But to the left, we'd be approaching 0. Why don't we try this? 5x cubed plus 3e to the x, e to the x plus 6x cubed. Okay, why don't you guys find the horizontal asymptotes for this guy? let you know right now there are two answers that are different. Two answers are not plus or minus 3. They are two different numerical answers. If you just got 3, you're missing the other side of things. I don't think I've seen anybody get both of them yet. Zero is not the answer. 3 and 5/6 is the answer. What? Everybody gets the 3, right? If you're looking at positive infinity, you could cross this guy out, cross this guy out. And now, in this situation, we do have the same growth. So again, instincts, those cancel. You just get 3. Don't plug in infinity when you don't have to. But it's the other direction that we are struggling with. If I plug in negative infinity, we have e to the negative infinity, e to the negative infinity. That's 0. That's 0 growth. So, e to the negative infinity, toss it out. Cross that out. It's 0. This simplifies to 5x cubed over 6x cubed. There it is. So we have two horizontal asymptotes for this function. To the right, we're going to 3. To the left, we're going to 5/6. All right, enough about horizontal asymptotes. Let's talk about the vertical asymptotes. Okay, so we talked about end behavior. Now, let's look at the behavior around a vertical asymptote. Denominator equal to 0. Here, x minus 3 equals 0. If I get x is equal to 3. Whenever I have a number divided by 0, that is an indication that we have a vertical asymptote, VA for short. So we know that at 1, 2, 3, I have this dotted line, and my function is going to be approaching. Now, what we need to try to figure out is how. Is it going to go up to the left and down to the right? Are we going to go down to the left and up to the right? Are we going in both directions in some way, or the same direction in a specific way? So our goal is to figure out the behavior around this vertical asymptote. All right. Now, here is a new idea. If I take something, anything, let's take the number 3, and let's look at a series of fractions, like 3 over 1, 3 over 0.1, 3 over 0.0001, 3 over 0.00000001. As the denominator gets smaller and smaller and smaller, what's happening to those fractions? They're getting bigger and bigger and bigger. Okay? Now, if I had a negative 3, well, all of a sudden that would be a very big negative number, right? Now we are going to use notation for what we consider a infinitely small number like this 0.0001. And instead of writing out 0.0001 all the time, we'll just use a 0 to the left and a 0 to the right. Some books uses like an epsilon that we are adding to 0. Epsilon representing a very, very small value. But we'll just go with this. Okay? And we'll know of this as being a very, very small negative number. So we're approaching 0 from the left, something like that. And this is a very small positive number. You know, dots in here so that you know we have like an infinite amount of zeros before the 1. Okay? Well, if I have some number k, and k is a positive number, and we have something that is infinitely small underneath k. If I take this positive number and divide it by something small and negative, I'll get something large and negative. If I take this number divided by something infinitely small and positive, it's something infinitely large and positive. It's just keeping track of signs and understanding if we have something divided by something infinitely small. Okay, so here's the process. Let's go back up to the previous guy up here. Well, I understand that we have a vertical asymptote around 3. Now, of 3. Let's look at the left side. I'll look at the limit as x approaches 3 from the left of -2 over x minus 3. This is more of kind of a conceptual understanding using just your knowledge of what a number. I hope everything's still working. What a number to the left of 3 looks like. Well, on a number line, a number to the left of 3 is like 2.999. If I took that number and plugged it in for x, yeah, I'm getting very, very close to 0. Sure. But if I plug in 2.999 and subtract 3, it's going to be something very close to 0 and negative, because 2.999 is less than 3. If I take 3 away from it, it'll be negative. I have -2 divided by something infinitely small and negative. That is something infinitely large and negative. That is telling me that if I'm just to the left of 3, I'm going up. And I know I'll have something like that. I'm going to do the same thing to the right of 3. Thinking of a number just bigger than 3, 3.001. I think about plugging that number in for 3. That will give me a number very, very close to 0, but 3.001 is just a little bit bigger than 3. So it's going to be 0, but coming from the positive side. I have a negative value divided by something infinitely small and positive. I get something infinitely negative and big. So that means I'm going down. And all of a sudden I know my behavior. You can combine that with the fact that you know that we have horizontal asymptotes at 0 because we have growth in the denominator to kind of understand, at least in general, what your function might look like. All right? Where we have to be careful sometimes is, to the left and to the right of a negative value. I'm looking at -1 to the left. Obviously, we have -1 over x plus 1. We know that when x is equal to -1, I have a vertical asymptote. The question is, what is the behavior of my function around that? -1 from the left. Now, if I thought about 1 from the left, it's 0.99999. But -1 from the left would be -1.001. A lot of students make mistakes with that when we're on the negative side of our number line. Dungeon? Yeah. Nice. I hope you do well in this quiz next class. All right. Well, that's all we have to do. We think about plugging that number in there. We're going to add 1 to it. What do we get? Something infinitely small and negative or infinitely large and negative? Compare that with your neighbors. What do you think? We know it's a vertical asymptote. The question is, which way is our function trending around our vertical asymptote? Very, very small and negative. A negative divided by a negative, a positive. Something divided by something infinitely small, something infinitely large. So I know to the left, I'm going up. Okay, do the other side. I'm going down. Cool? Not that bad. Let's try this one. Now I have an asymptote of 4, but what's the behavior of my function around that asymptote? May I help to use a number line to understand what a value like 4 from the left is and what a value like 4 from the right is. Check your answers with a neighbor. Interesting thing about these is that I am squaring these very, very small values. So if I take something infinitely small and negative and square it, it's still infinitely small, but it becomes a positive. Negative times a negative is a positive. So this is a positive. So we have a negative divided by something infinitely small and positive. It's infinitely large and negative. Same thing would happen here, only the very small positive number would stay very small and positive. So I'd actually be approaching negative infinity in both directions. You will see in some cases that text will say if I looked at the limit as x approaches 4 in general of this, since they both agree with each other, you could negative infinity. Some texts will say, no, you can only have negative limits if you look at one-sided things, but some will say otherwise. It's not super important for you guys. Just if you see something like this, and you're like, but Mr. Messer, I thought you couldn't have a limit at a vertical asymptote. Well, you technically can. Okay. Now let's look at this one. X minus 5 over x minus 4. Where students struggle is they think, okay, 3.999, if I plug that in here and here, they're like, oh man, 4 from the left minus 5. Is that minus 1 from the left or right? And I know this 3.999 minus 4, that's going to be 0 from the left. But turns out you shouldn't care about the numerator and about from the left and from the right of numbers other than 0. Why shouldn't I care if I have, say, negative 1 from the left and from the right in this situation when I do care if I have 0 from the left and from the right? Discuss that with your neighbors. Anyone from this corner? It's you, Mr. Wolf, what do you think? Sweeler? Chesney? Schwitters? Yoder? More? Sardi? Michaels? McDonald?
So minus 1, I mean negative, by the way. 0, so it would be positive or negative. On what side it's not.
Doesn't matter if I'm negative 1 from the left or negative 1 from the right, it's still negative. Okay? So this doesn't matter. It's still going to be very, very close to negative 1. But when I'm close to 0, it matters a big deal because it's a positive or a negative depending on which side you look at. So I could have literally just plugged in 4 here, not cared about 3.999. But here, make sure you care about the 3.999. So you get negative 1 over something very small, and negative, you get something very large and positive. Okay, do the next one. Now that we know that if you get something other than 0, you don't care if it's from the left or from the right. I think my microphone went out. I'm kind of sad. We'll find out. Okay, so I plug in negative 3 from the right. It doesn't matter. I still get negative 2 when I add 1 to it. Okay, it's a negative value, either if it's from the left or from the right. In the denominator, negative 3 from the right, negative 2.999. That makes a difference. You get 0 from the right. We understand that around the vertical asymptote, negative 3, to the right of it, I'm going down. Negative 3 plus 1? Oh, you guys got a 5 up here? Okay. Well, that's a positive too. And that's a positive. And that's Are these the same for you as for me?
Yeah.
-2 from the left, 3 from the left. Okay. This is an interesting one. It's important to have a good understanding of what a number to the left of -2 is, like -2.001. If I plug that in for x and square it, I'm going to get a number close to 4. You and your neighbors discuss if it's bigger than or less than 4. It's a little bit bigger on the negative side. Squared will be a little bit bigger on the positive side. So this will be that guy and that guy. Do the next one. So this is not -3 from the left. This is 3 from the left. So 3 from the left. 2.999. If I took 2.999, plug it in here, I'd get something a little bit less than 9 after I square it. Subtract 9 from that. We have something a little bit bigger than 0, positive. But if I plug 3 into the numerator, multiplied by -2, that'll be a number close to -6. So all in, we're approaching negative infinity. Okay? Behavior around asymptotes. Well, let's do some stuff with trig functions. Trig functions sometimes have asymptotes. 1 over cosine x will have some vertical asymptotes. It will have a vertical asymptote at pi over 2 because the 1 over cosine of pi over 2 is 1 over 0. You have 1 over 0. That's an indication of a vertical asymptote. Well, the problem is, am I going to be approaching 0 from the left or from the right? How are we going to get there? Well, here's my advice, because these are somewhat tricky unless you do the following. First, start with a number line. Start with pi over 2. Include the values that you know on the unit circle that surround pi over 2, like 0 and pi. Okay? Now, if you are pi over 2 from the left, that's like coming from 0 and traveling to pi over 2. Here's pi over 2 from the left. Then you are going to translate this number line into our unit circle, where I have 0, pi over 2, pi, 3 pi over 2. And locate that angle measurement on the unit circle. Pi over 2 from the left would be here, coming from 0, traveling to pi over 2. Now, understanding either cosine being your horizontal distance, going to the right is positive, left is negative, same with sine going up and down, or remembering your mnemonic friend, all students take calculus. This is telling you that cosine in the first quadrant is positive. And as I get closer and closer to the angle measurement of pi over 2, these horizontal distances get smaller and smaller and smaller, approaching 0, but they are positive. So I am approaching 0 from the positive direction, even though I'm approaching pi over 2 from the negative direction, I guess. And that is a positive infinity. You guys try that with 4 over sine pi. Check your answers with a neighbor. So what I do is I have pi here. I know it's coming from 3 pi over 2 to pi is pi to the right. Okay, coming from 3 pi over 2 headed towards pi. So that puts me in the 3rd quadrant. I'm a little bit more than pi. I'm coming from 3 pi over 2, approaching pi. I know the sign of pi is 0. Okay, so that's important. Make sure you get 0. So I have 4 over 0, but 0 from the left or right. Well, in the 3rd quadrant, distances in the 3rd quadrant are going down. So I'm approaching 0, but all of my sign values are negative, and we're approaching 0 from the negative side, which means around this asymptote, we're approaching negative infinity. Okay. Do these 3. Go. Turn the 3rd one into pi from the left, because we already did pi from the right. We got 0 from the right, 3 pi over 2 from the left, pi from the left. Again, it helps to use a number line. This is 0 from the right. Three pi over 2 from the left. Pi from the left. Yep. It's just a mnemonic to know which trig functions are positive in which quadrant. So the 1st quadrant, all trig functions are positive. The 2nd quadrant, only cosine and its reciprocal positive. Sine and its reciprocal. Right. And then the 3rd quadrant, take, tangent, and cotangent are positive. And the 4th quadrant, calculus, cosine, and its reciprocal. Yep. Get positive for all three of them. Positive infinity for all three. I just changed it to pi from the left because we already did pi from the right. If you did pi from the right, it would have been a negative, yes. Okay? Second one, it's -2 over something infinitely small and negative. 3 pi over 2 from the left. We're coming from pi going to 3 pi over 2. Puts us in the third quadrant. When we are in the third quadrant, cosine values are negative. So I'm approaching 0 from the negative side of things. Okay? Last two. Cotangent as x approaches pi from the left, and x secant pi x as x from the right. Check your answers with a neighbor.
Then we're going this way. I know.
So if I'm approaching pi from the left here, and I know cotangent is cosine over sine. Pi from the left, coming from pi over 2, traveling to pi, puts us in the second quadrant. Now, first of all, the cosine of pi is -1. And we're trying to find the trig function of these values. The cosine of pi is -1. The sine of pi is 0. But as I get closer and closer to pi from the left, and I'm in the second quadrant, sine values in the second quadrant 0 from the positive side. That is why I have -1 over 0 from the right and I have negative infinity as my answer here. For the second one, I'm plugging in 1/2 from the right, but it's 1/2 times this pi. So you can think of it as pi over 2 from the right. Coming from pi, going to pi over 2. Coming from pi, going to pi over 2 puts you in the second quadrant again. Cosine values in the second quadrant are negative. The numerator is going to be an x. The secant can take the reciprocal of the secant to get cosine. Plug in the 1/2 in for the x. Plug in the 1/2 here. Cosine of pi over 2 from the right. Cosine values are negative in the second quadrant. You have a positive value divided by something infinitely small and negative. You have something infinitely large and negative. All of these take practice to master, but that's horizontal and vertical asymptotes.